once again with the description of a standard 52 card deck. So each of the 52 cards is distinct. Cards come in 4 types: clubs, hearts, diamonds, and spades. So there are 13 cards which are clubs, 13 cards which are hearts, 13 cards which are diamonds, 13 cards which are spades. So you have a ace of clubs, 2 of clubs, 3 of clubs, 4 of clubs, 5 of clubs, 6 of clubs, 7 of clubs, 8 of clubs, 9 of clubs, 10 of clubs, jack of clubs, queen of clubs, and king of clubs. Similarly, you have an ace of hearts, 2 of hearts, 3 of hearts, and so on. Okay, 52 distinct cards, 13 cards of each suit: clubs, hearts, diamonds, and spades. And then within each suit, you have an ace, 2, 3, 4, up to the king. Okay, so that's what a standard 52 card deck looks like. Some decks will also come with cards called jokers, which are usually which may or may not be used in a card game, but we're not talking about those when we talk about the 52 card deck. So how many 4-card hands are possible? In a hand, we don't care about order. Okay, and that's for you to decide whether to put the card here or put the card there in your hand. All right, so how many 4-card hands are possible? Okay, the assumption is that all getting any card is equally likely. So all the 4-card hands are equally possible. So by our discussion before, if all 4-card hands are equally likely, then what we want to do is this idea will be used when we want to calculate the probability of getting a particular 4-card hand. Okay, so how many 4-card hands are possible? Well, what you have to do is remember our discussion of partitions before. You're going to partition your cards into 2 sets, and the ordering within each set is not going to matter. So you're going to put 4 cards here. This is the hand that the dealer gives you, and then the other ones. And the ordering in that hand doesn't matter, and the ordering in the cards that are left over doesn't matter. So that's a partition. And remember, so we recall our idea of a partition. So 52 choose 4. Right? Take 52 cards, distinct symbols. You're going to put 4 of them in one pile, and you're going to put the remaining 48 in the other. And we have this notation here: 52 choose 4 to represent that number. Okay, once again, what is it in terms of factorials? That's 52 factorial divided by 4 factorial, and then divided again by 52 minus 4 is 48 factorial. Okay, so that's the number of 4-card hands. Okay, what is the probability of being dealt fairly the 4-card hand, which consists of the ace of clubs, the ace of spades, the queen of clubs, and the queen of spades? Okay. Remember, there were 52 choose 4 card hands, and in a fair deck without the dealer cheating or the player cheating, any 4-card hand is equally likely, right? And the hand that we've described is exactly one of those hands. It's exactly one of the possible combinations of hands that you could have, 4-card hands that you could have. So if all of the outcomes, if there are 52 choose 4 possible outcomes, there are 52 choose 4-card hands, and what's the probability of getting exactly one of those? From our discussion before, that's 1 out of 1 divided by 52 choose 4. Now, what about a 4-card hand? What's the probability of getting a 4-card hand consisting of the 4 queens? Well, it's really the same discussion. That is, we have exactly one 4-card hand, which consists of the queen of clubs, the queen of hearts, the queen of diamonds, and the queen of spades. That's exactly one 4-card hand. So that's one result out of how many possible 4-card hands are there? 52 used for. So the probability of getting this one exact 4-card hand is 1 out of 52 choose 4. As before. Okay. Remember, the probability of any particular 4-card hand is 1 divided by the total number of 4-card hands, because they're all equally likely. 1 divided by 52 choose 4. Okay, what's the probability of being a delta 4-card hand consisting of the 4 queens? Or, so you either get the 4 queens, or you get the 2 of hearts, 3 of clubs, 4 of spades, and 5 of diamonds. Well, we had that discussion before, right? If we had small n possible outcomes, so the event consists of the small n possible outcomes. There are capital N possible outcomes, and all the events are equally likely. Then it's small. Then that probability is small n divided by big N. So here we have 2 possible outcomes. This event consists of 2 possible of the possible outcomes, right? And the probability of any one possible outcome, they're all equally likely, is 1 divided by 52 choose 4. So the probability we're being asked for now is 2 times 1 over 52 choose 4. Okay. So, yeah. All right. What is the probability of being dealt a 4-card hand consisting of the ace of clubs, the ace of spades, the queen of clubs, and any heart card? Okay. All right. So there are 52 choose 4 possible 4-card hands. They are all equally likely. So here, n is equal to 52 choose 4 in this case. What's your small n in this case? This event that you're describing, how many elements are there in this set of possible events? Well, you have the ace of clubs is fixed, the ace of spades is fixed, the queen of clubs is fixed. And then you could have, in your hand, you could have either the ace of hearts for the 4th card, you could have the ace of hearts. Or you could have the 2 of hearts, or you could have the 3 of hearts, and so on up to the king of hearts. You could have 13 heart cards. Okay, so in this event that you're talking about, this collection, this set of possible events that you're talking about that are being described here, there are 13 such. There are 13 such elements. Okay, so there are 13 possible. Here you're talking about 13 of the possible outcomes. Out of 52, choose 4 possible outcomes, and all of the outcomes are equally likely. So by our previous result, this probability is 13 out of 52 choose 4. Out of 52 choose 4. Okay. So now let's look at this. Again, you're being dealt a 4-card hand. There are 52 choose for equally likely 4-card hands. What's the probability of getting 2 of the aces, 1 of the kings? So 2 of the 4 aces, 1 of the 4 kings, and then some other card. Okay, which is not an ace and not a king. So you're going to get exactly 2 aces, exactly 1 king, and some other card which is not an ace and not a king. Okay. Well, if we can, so there's a set A which consists of all of the possible outcomes which meet these requirements. And then there are 52 choose for possible 4-card hands. And from the theory that we have, the formulas that we have for equally likely outcomes, this will be the probability we're looking for is the number of elements of A, the cardinality of A, divided by 52 choose for. So how many 4-card hands are there that meet these requirements? Okay. I want to think about that for a moment. Okay. Right. So once again, there are 52 choose for equally likely 4-card hands. All of them are equally likely. Okay. So now you're going to be doing your partitioning. And you can think about, let's do these rules of counting. And we're going to construct this hand. So how do you do it? Well, you have 4 cards. You have 4 aces. You have to choose 2 of them, right? Then you have 4 kings, and you have to choose 1 of them. Then you have to choose 1 card from the remaining cards. And those cards can't be aces and can't be kings. So you have to choose, out of 4 aces, you have to choose 2 of them. Out of 4 kings, you have to choose 1 of them. You've used up 8 cards, right? And now there are 44 cards left over, and you have to choose 1 of them. So how many ways are there of doing this? Well, that's our rules of counting, right? So our multiplication rule. So 4 choose 2 ways of choosing the 2 kings. And then we're going to choose 2 kings, and then we're going to choose 2 aces. That would again be 4 choose 2. I think I made a mistake here. All right, no, all right. So we're supposed to be receiving. Sorry, we're supposed to be getting 1 king. So this should be 4 choose 2 to get the 2 aces. 4 choose 1 to get the 1 king. And then 44 choose 1. Okay. So this will be 4 choose 2 times 4 choose 1 times 44 choose 1 divided by 52 choose 4. Okay, so we have a fair 20-sided die. It means that all the numbers 1 through 20 are equally likely to come up. What's the probability of giving an even number? Okay, well, how many even numbers are there? 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So there are 10 such results that meet the requirement, and they're all equally likely. So 10 times the probability of any result, and any result is 20, 1 out of 20. So 10 times 1 over 20, 10 over 20, 1/2. Okay. Seems to make sense. Okay. 2 cards are dealt from a standard deck of 52 playing cards. What's the probability that both the cards are kings? Okay. So how many all 2 card hands are equally likely in a fair deck. Assume that the deck is fair. There's no cheating going on. So the probability of any 2 card hand is 52 choose 2. Okay. Now, how many ways are there of getting 2 kings from 4? Well, there are 4 choose 2 4 card hands that have 2 kings. Right? And you don't need to choose any other card. So this is a 1-step process. Out of 4 kings, you have to choose 2. So the probability is 4 choose 2 divided by 52 choose 2. Okay, the text by Walpole has a number of nice problems that are related to equally likely probabilities in various situations. So I would suggest that you review a few of those. Okay. See you next time.